Hello, everyone. Thank you for joining, and many thanks to Michu for her kind invitation as well as the nice introduction. Uh, so if we were meeting in Toronto, I would say good morning to everyone. But now that we are spread all over the world, I would say hello and welcome. Michu talked about the title of the talk. So I will try to keep the talk at broad high level so as to provide you with some design considerations as you proceed to develop new machine learning models in mHealth. So before I proceed to describe the content of the talk, I would like to acknowledge our National Institutes of Health and National Science Foundation in the US, whose funding has largely supported the work that I'm going to describe. So this is a general knowledge that, but I just want to make sure we are on the same page. So the wearable sensors and sensors in the smartphone, they can be used in a variety of ways. And when it comes to tracking of health and wellness, we can use them to monitor exposures to various environmental cues or risk factors. We can also use them to monitor daily behaviors, which are other risk factors for health and wellness or adverse outcomes in health. And interestingly, we can use these very same sensors also to measure some of the outcomes. And so measuring all these three together, all on the same platform concurrently, at a fine granularity of time, makes it a very powerful tool. So with this tool, we can detect adverse health events. And once we detect the adverse health events using other markers from the various sensors, we can also predict these adverse health events in advance by finding signatures in the sensors that precede the detection of adverse behaviors. And once we have a reliable, robust prediction that works in the natural field environment, or even when we have a reliable detection, we can use either of these two to launch a just-in-time intervention meant to help people keep their health and maintain wellness. So if we are able to do so, then we can make a huge difference in the health and wellness of our entire society. It has been shown that we can, 75% of healthcare spending today goes into the chronic diseases. You could say, more, and it's only going to increase because with higher or increasing life expectancy, more and more people are expected to live with this chronic diseases. But it doesn't have to be that way. If we can help people maintain healthy behaviors, then we can bring down the chronic disease incidence as well as its prevalence. It has been shown that if we could convince or help people stop smoking, start eating healthy, and be physically active, it can cut down 80% of type 2 diabetes, 80% of cardiovascular diseases, and 40% of cancer. So there is a tremendous difference that we can make by being able to provide technology that is efficacious in helping people maintain healthy behavior. So what I'm showing here is our experience in developing various markers of health and wellness that we have developed from wearable sensors, and that's what I will draw upon during my talk. So we have worked on stress, detecting stress, then detecting smoking, detecting conversations, detecting cocaine usage, detecting craving, detecting brushing and flossing. And so I will use a subset of these to draw upon some general guidelines. You'll see multiple papers and papers spanning almost a decade. That's because our goal in developing each of these markers has been that we want to see them used in real life. And so on the stress, we started working way back in 2007. And we still continue to work on it because we haven't seen it yet widely deployed. And throughout the talk, I'll describe the process that we have gone through and what roadblocks still exist. And so we have been fortunate to have some of these markers deployed nationwide in various scientific field studies by health researchers. So what we show here is a subset of those studies and the size of the data sets that we have collected. And as I'll describe, we are still, this journey has not concluded. So we are still on the, continuing to make progress. So when I think about the mHealth markers that we have developed, I broadly divide them into 3 stages: the data collection, modeling, and then evaluation. And our eventual goal has been to achieve the achieve the sensitivity, specificity, generalizability, and reusability that is a must to have the clinical utility. So we have worked with a wide variety of health researchers, clinicians, and behavioral scientists we have learned some lessons as to what might help each of these markers achieve clinical utility. So let me start with the data collection. So when we think about data collection from a researcher side, as I show on the left side, there are different considerations. Should the data be collected in the lab or the field setting? What should be the data size? What should be the diversity in terms of the data, in terms of participant selection, in terms of scenario that is covered? Which sensors should be used? What should be the experiment duration, right? And then how should the data be prepared? How should labels be collected and assigned to the data? But then when we do any of the experiments, it's not only the experimenter who does the hard work in collecting this data. It's also the study participants who do equal amount of hard work and sacrifice for, in the greater benefit of science. So as the experimenter, we also need to keep their issues relevant in mind. So we should do our best to minimize the burden to them. It should be no more than it has to be. Interruption, whenever we ask them to do something as they are going about in their daily life, that is also a major burden, and we should try to minimize them while still being, collecting the labels that we need. They should be compensated for their time and effort, but not overcompensated, and that might compromise the study goals. And then it's great if during the experiment or during the study, the participants see some personal utility of participating in this data collection. And we should try to make it engaging. Again, that will reduce the burden and increase the chances that they'll contribute good quality of data. And because many of these experiments are done in the natural field environment where sensors collect data continuously, and as we have now seen, that these sensors can reveal a whole variety of daily health and behavior states, and therefore, some of which can be privacy sensitive, and therefore privacy of the participant should also be a prime consideration, and we should provide them tools to manage their privacy while they participate in data collection. So I'll now use a few examples from our experience to see as to how we have gone about them. The first is, the stress assessment. So as I mentioned, we started this work way back in 2007. It took us a few years to develop the sensors and then to design the right experiments. So the issue here in sensors, our first observation was what sensor should we use? So and by then there were a lot of, so stress has a 100-year plus history of research. And so a lot is known about stress, largely from either the lab studies or self-report collected in the field. And then some of the ambulatory sensors were also deployed in the field. So what is known is that stress triggers physiological response, but we also know that the physiology is affected by many factors and not just stress. Physical activity, change in posture, speaking, eating, caffeine, alcohol, all of them, they affect physiology in various ways. and medications. So how do we separate out the changes in physiology that is due to stress and isolate them, and be able to recognize when the changes in physiology is due to stress and when it is not? The second issue also is that the stress does exhibit physiological response. But when we ask people to provide self-report, the self-report is usually retrospective. That means the stressors may have occurred some time ago, but their perception still is there with the person. So you may have heard of your paper acceptance or non-acceptance or proposal acceptance, non-acceptance, 2 hours ago. But if we ask you now, you may still have some sense of being stressed. So the physiology would have recovered long ago, when you first heard the news, but then the psychology takes a lot longer. So how do we map this physiological response to the psychological perception of stress? So these are some of the challenges in developing this detection of stress. So what we did was that, the prevalent method in the field to assess the stress is to collect self-report. But as I mentioned, there is a wide discrepancy in self-reports. Self-report have noise, they have wide variability, and they have this time lag. So we wanted an unambiguous label for our data set. So for that, we conducted a lab study. And in the lab study, we used 3 different diverse stressors: a psychological, a psychosocial stressors, a cognitive stressor, and a physical stressor. And to create some diversity of what participants will be expected to do in the natural field environment. And what you see at the bottom is the stress protocol that we used. And we also collected self-report 14 times and denoted by those dots in the timeline. And so what we did was that instead of treating the self-report as our label, we treated the lab protocol as our label. So that means when participants were doing public speaking or preparing for public speaking, those are the data sets collected during those moments is what we considered as the participants being stressed. When they are under baseline or under recovery, we coded them or labeled them as not stressed. We did so because these 3 stress challenges have been shown by many different methods, both from the physiological measurement as well as from hormonal measurements, like using cortisol, that they universally do stress out most of the participants. So this provided us with a clean label, unambiguous label. But when we go to the field, we cannot ask people to do these steps. So in the field where people are living their natural life, we are limited to collecting self-report. But field study has much greater ecological validity because it captures the natural environment. So to have sufficient data from each participant, we did ask participants to report 10+ times daily. In some cases, when we had a 2-day study, we asked them to report about 20 times a day so that we had sufficient labels for each participant. And what you see at the bottom are the questions we ask. So none of these questions really are just about stress, because when it's about self-report, we need to approach it from many different angles to have sufficient robustness and to see if there is consistency in these items. That means whether the participants are paying attention when they're filling out these surveys. Okay. So next example I will use is detection of cocaine use. So cocaine use does affect physiology again. But then the issue of cocaine use is that depending on how participants intake cocaine, the onset of action, that means how long since the intake do we begin to see the effect in physiology, when is the peak effect, and how long does it last, they all differ depending not only on the modality, but also the dosage. And when people, if we collect only self-report labels from participants, ask them to report as to when they took cocaine and how they took it, again, we will have noisy labels. So what we did was to develop a model. We conducted a lab study. So Johns Hopkins Medical School has a residential facility where they can keep participants for weeks. And so in there, we had participants wear the sensors, and then they were given an opportunity to self-administer cocaine. And so when we did collect this data, we also had the participants keep wearing the sensors when they were doing the regular activities, and those we knew that exactly when cocaine was administered, and we knew when we could be certain that cocaine was not in their bloodstream. So and then we repeated that experiment at the NIDA intramural research program as well. And so we had a wide variety of dosage administered. Now, when it comes to the field setting, we recruited 42 drug users. They used to visit lab daily, and they wore the sensors for 4 weeks in the field, and they self-reported when they used the drugs and how long ago was it. But we needed some other verification as well to figure out. They could forget to report that they used cocaine or not report that they used cocaine, right? So how do we figure out as to which days that they did not, or they confirmed not to use cocaine? So for that, we had a regular urine test done as well. And any uses of cocaine, usually has traces in the urine for 3 to 5 days. So this is what we did to have labels that can cover our data collection and verification from multiple sites. Third example I would use is an objective event. It's a smoking. So we noticed that we could use respiration and hand-to-mouth gestures to detect smoking. Respiration because people usually take deep breaths, deep inhalation and exhalation when they take a smoking puffs. And hand-to-mouth gestures because smoking involves taking their hand to the mouth. And if we look at some clean data, we can see that the puffs are a little different in both respiration as well as they are in the hand-to-mouth gesture. But then, if we think about hand to the face or to the mouth, more than 200 times a day. Perhaps less now in this pandemic, as people become more aware that you should not be touching your face that often. But still, it's in few hundreds. And if we think about the breath cycles, that's more than 15,000 a day. So what it says is that we need data sets that can give us fine-grained labels, unambiguous fine-grained labels for us to develop a model that can indeed work in the field environment. So what we did was that we did data collection again in a closed setting. That means when we could have an observation, and then we did a field study as well. So in the lab study, or it's not lab study, it was a controlled study. So that means the participants were asked to visit the lab, and when they visited the lab, we had a marking of each puff. And that marking of each puff was done on the same phone that the participants' sensors were transmitting the data to have time synchronization. And the marking was done by an observer who was sitting at a little distance so as to allow the participant to smoke freely as they would in their natural environment. We also used a smoking topography device that marks the timing of each puff. It's an expensive piece of equipment costing several $1,000s, but because it had the potential to give us the timing of each puff. Later on, it's called Crest Pocket, and we couldn't use the data from Crest Pocket because the time synchronization of the Crest Pocket has so much variability in terms of clock drift that it was hard to align it to each of the puff timings. So then for the field setting, what we did was we had a smoking cessation study. So that means participants were, wore the sensors 1 day before quitting and 3 days after quitting. And each day that they were doing, they had this, they were in this study, they visited the lab, and in the lab of course we asked them to self-report any time that they smoked, but we also had biochemical verification. That means we had them blow into a CO monitor when they visited the lab so as to confirm whether in the past 24 hours they had smoked or not. So that gave us a verification of their smoking status. So then the final example I would use is for detecting brushing and flossing. So the smart toothbrushes, they are able to help people brush appropriately. They can guide the their users in both monitoring how well they are brushing and when they are brushing and how long they are brushing. But more than 80% of the population even in the US uses regular toothbrushes. So we wanted to see if by using this increasingly popular wrist-worn trackers or smartwatches, can we detect brushing and flossing just by looking at the gestures or inertial sensor data from these smartwatches. So the challenge for us was, how do we design the study so that we have the right labels? Okay, so what we did was that after a significant debate here in smoking can happen any times of the day, but brushing usually happens in the bathroom when people are in front of a mirror usually, and it happens at certain times of the day. So what we did was that we had implemented a video capture on the smartphone, and we provided the participants with a mounting device so that at the time of the brushing, they fixed the smartphone on the mirror so as to capture the video during brushing. And this video capture was just during brushing, and so therefore it didn't involve as much of the privacy issues. At the same time, it was able to give us the time synchronized measurements because video and the sensor data was being collected on the same smartphone. So, and for assessment of false positives, we assume that when they were not reporting this brushing, then they did not have a brushing episode. So, and largely when people are out and about in their daily life, unlike smoking, they may not be brushing or flossing. Okay. So our key lessons in the data collection was that we need to have the label correspondence with the event, and many times labels can help. Getting unambiguous labels sometimes requires a controlled lab study, but field study is needed for ecological validity. And as I'll explain, and given that what I've seen in some of the papers, labels, they rarely correspond to lab, and so we need to have explicit model adaptation. But some of the approaches that are coming out in some of the works is that people build a whole different new model. That means they train a new model for the field study data. If so, then the lab study is not of great use, and then you don't have either the ecological validity of the model that was developed from the lab data, or the physiological validity of the model that is collected in constructed from the field data. So my suggestion would be to use the lab data to develop the base model and find the right adaptation to map the labels from the lab to the field, but not develop an entirely, develop an entirely or train an entirely new model from the field data if you are doing the lab study as well. I'll explain a little bit more. So when it comes to modeling, there are several key considerations here as well. Should you be doing a state estimation or event detection? And then, should you be doing sliding windows or doing it on independent windows? Feature engineering itself is a big challenge, largely with respect to what data, what pre-processing should be done, what post-processing should be done, what features should be discovered. whether data-driven or or domain science-driven. And then whether whether the model has sufficient interpretability or explainability, which may impact the generalizability as well. And generalizability of the model also depends, from lab to field and across subject, situation, and events. How do you handle the poor quality or missing data? Because when you're collecting data from the natural environment, especially when these are physiological data that require bodily attachments, that there are lots of issues with respect to the quality of the data. And finally, if we want our models to work in real time, in real life for people, then the models should be computational feature as well. So for our first example of a stress modeling, so of course, we had the issue of noisy physiological sensor data. Then there is wide between percent variability in baseline and in reactivity. Somebody's resting heart rate is 50, somebody else is 70, right? And given the same stressor, different people react differently. Then, as I mentioned, we have several confounding events that can also change, excite physiology. And how do we isolate the effects of those confounding events? Then, when we are comparing with self-report, there is noise, ambiguity, and variability in self-reports. And then I talked about there is a temporal lag in the correspondence between physiological response of a stressor and the perception of a stress that is captured in momentary self-report. So the model we developed, so first we had an elaborate quality control. That means for each of the sensor data, we had to assess when is the sensor data shows sufficient sufficient waveforms that is a legitimate either the QRS complex or the respiration waveform. And unless it conforms to the morphology, then it was not admitted. So then, how much of the data should we have, or usable data should we have in each minute for this minute to be used for further processing or for feature extraction? And then for normalization or to account for between percent variability, we normalized each of these features to the Z-score for that individual, so that it can account for their respective baselines and their reactivity. And then to take care of, because there are several outliers, there's also the capping that we had to do of these various features. And then because of the unbalanced data set, there was optimization of the upper parameters. And finally, our solution to the confounding events was that when there was physical activity, sufficient physical activity on the torso that can affect the physiology more than can be affected by stress, then we suspended the assessment of stress. And not only when there is physical activity, but we also allowed for some time for the physiology to recover, because it takes a few seconds or sometimes even 2 minutes for physiology to recover after physical activity. Then, so what our model provides, this support vector based model, is a stress likelihood time series. And so, as you can see, of course, it's not perfect, but largely, we use a threshold to classify stress or not stress. But in general, we can use this binary classification threshold for this output, and this is a state model. Right now, so this model produces this output for every minute. So we can also, this by itself has a lot of output throughout the day, right? So there is 60 minutes in an hour, and in 10 hours, there are 600 minutes. In 16 hours, there are close to 1,000 minutes. So we have this 1,000 outputs. If clinicians want to use this output of stress to trigger an intervention, then it's too many decision points for them, right? And if we can interrupt a person or launch an intervention for only a few times a day, otherwise it will be annoying, then we need to select those 2-3 opportune moments. And so we need a method to select those, few opportune moments out of this 1,000 likely or candidate minutes. So for that, we use this stress likelihood time series, and we use a moving average convergence divergence method to locate the stress episodes. That means those periods when the stress likelihood is elevated and remains elevated for some time. And so that provides us with major stress or significant stress episodes, which can then be used for intervention. And then, the intervention could be either proactive or reactive. And as you see on the right side, those are various moments. Of course, at A, we have to do the full prediction of, is this going to be a major stress episode? Becomes a little easier when we are at the point B, more easier when we are at the point C, and certainty when we are at the point D. And so, so there is a trade-off in how soon you can launch an intervention and how certain you can be. So for moving on to the cocaine detection. So in the cocaine detection, we had different challenges. So first challenge is we had this art-wide for cocaine detection. And so from that, that's again is a noisy time series, especially the data we get from the field. So we had to do a time series pattern mining. Second, basically to find out from when did the effect of cocaine begin to show in this R2I interval, and when did it end? So we needed to isolate that window. For that, we needed to identify the start and end of the cocaine effect in physiology. Second issue is this: there is wide variation in dosage and modality, as I showed. The dose, so modality, so in the lab, we only had intravenous administration of cocaine. But in the field, people could use smoking, sniffing, ingestion, and so on. In terms of doses, we could only provide up to 40 mg in the lab. In the field, they had 400 mg, even some of them even had 600 mg. And we couldn't administer those high amounts of cocaine in the lab. So, and then we had no, the participants in the lab were different than the participants in the field. So we had no field data for those participants who were in the lab. The final challenge was that the physical activity also excites physiology quite a bit, almost at a similar scale as that from cocaine. And to compound this problem, it's not that when people take cocaine that they sit idle. They even get, they even begin furious walking, some of them. So you have to not only, so the solution we had for a stress that when there is physical activity, we suspend the assessment of stress, that will not work here. We need to account for the effect of concurrently happening physical activity and still being able to say whether they, when are they, when is there sufficient cocaine in the bloodstream. So our overall modeling approach here was that we, of course, had to do data cleaning. So detect R2I intervals and remove the outliers. And then we had this idea about locating the candidate segment. For that, we first did a smoothing, then we identified the window, and then did the pre-screening. So smoothing, we found the right parameters for smoothing. The identifying window, for that, we again use this idea from the stock market analysis, where also the stock trading data, especially collected at this minute-second level granularity, is highly varying, right? But traders are still able to find those, buying and selling opportunities, and so they use this moving average convergence divergence approach, and that's what we use to on this smoothed time series to locate the major changes or shift in the signal in the R2I intervals that can mark the start and end. And after that, we did pre-screening, so that because there are lots of small changes, meaning the changes that do last for only a few minutes, right? Or that are not, significant enough, that means not, large enough to be likely from cocaine. So then we use only those that are likely to be from cocaine or from physical activity. After that, we had to isolate this effect of cocaine from concurrent physical activity. So as I'll describe next. So what we did for that was we, so this is the average convergence divergence idea I was talking about to isolate the boundaries. And so for the, for this, isolating the effect of physical activity from cocaine, we went back to physiology. So the autonomic nervous system, as you may know, has this parasympathetic nervous system and sympathetic nervous system. This is responsible for regulating the cardiac functions, which is what we were measuring, the cardiological, cardiovascular response. So PNS is responsible for conservation of energy. That means whenever there is increase in heart rate or respiration rate, it tries to bring the body back to baseline. And sympathetic nervous system is the one that elevates these heart rate or blood pressure and cardiac output to give us the energy we need during flight or fight situations. And so what cocaine does is it activates the sympathetic nervous system. And that's what is shown in this increase in heart rate. But so does the physical activity that also activates the sympathetic nervous system, the SNS. So when there is no cocaine and then there is physical activity, so SNS is activated. When the physical activity concludes, then the PNS kicks in. Then the PNS is the only one active. Otherwise, as soon as SNS gets activated, PNS also gets activated to keep the increase in check. But when the SNS role is done, PNS continues to be active. And at that point, PNS is the only one that tries to bring the body back to baseline. So when there is cocaine also in the bloodstream, then even after the physical activity stops, but the SNS does not stop because there is cocaine in the bloodstream and that continues to activate the SNS. So that means that recovery from this high heart rate is dampened because of the cocaine in the bloodstream. And the second part is that the amount of cocaine left in the bloodstream that decreases exponentially as per a drug absorption model. So that means the dampening that is due to cocaine, that itself decreases following a dynamical system model. So that's what we did to develop a model for the cocaine detection. So for smoking, so here the challenges were that the smoking is for a very short duration. Each puff only lasts for 4 seconds. There are 15,000 breaths in awake hours and 200 hand-to-mouth gestures, and there is wide variability in how people smoke. And depending on where they are, what situation they are, the gesture changes, and people hold the cigarette differently. And then there are other reasons: eating, drinking, yawning, for which people take their hand to the mouth. So for the modeling process in the smoking, we again first approach was to remove outliers and impute missing data. But after that, we located and marked the candidate windows. So that means hand-to-mouth gestures that are likely to be to represent taking the hand to the mouth, staying there for a few seconds, and then bringing it down. That is observed during smoking. And then, so similar to the cocaine model, we screened for these hand-to-mouth gestures that had sufficient duration and height and had the right hand orientation. And then we selected the candidate respiration cycle that corresponds to that hand-to-mouth gesture, and then computed the features, put them in the SPM classifier to detect each puff. And once we had the puffs, then the post-processing to discard any of the isolated puffs, because we expect puffs to be in sufficient succession that are few, maybe say 20, 30 seconds apart. And usually a cigarette lasts about 6 minutes or so. So we expect the number of puffs to last sufficiently long. So finally, for the brushing and flossing, so each of these events, smoking is a rare event, but brushing is even a rarer event. So if we assume 16 awake hours, then if we assess every 2 minutes to be because it's about 2 minutes that people are expected to brush. If we assess every 2 minutes in the day for whether they are brushing or not, Then what we show is that if you have 15% false positive rate, we can declare 72 brushing episodes a day. Even if we had 1% false positive, we can declare 4 false positive brushing episodes per day. So that means, I mean, for rare event detection, our false positive rate really has to be low. Then there is an issue of watch mounting on the wrist, because I mean, depending on how we wear the watch, the XYZ axis can be oriented differently. And then we need to estimate as to when does the event start and when does the event end. So for this process, we followed a similar approach of finding the candidates. We use the video data to locate the start and end for labeling. And then the candidate selection was necessary. Otherwise, there were so many hand-to-mouth gestures. And using this method, we were able to reduce the number of candidate segments that ultimately is provided to the machine learning model training to about 100 candidate segments per day. Otherwise, there will be, I mean, few thousand, about 1,000. So it reduced the amount of training data, and that reduced, in my opinion, the load on the, or what we expect the machine learning model to do. And that way, I think we were able to achieve sufficient accuracy. So the key lessons is that we first need to decide whether we want to approach a marker as a state or event. They both do require continuous assessment of a stream, but as I showed for the stress case, we can sometimes compose the events out of the states. Handling of confounding events is important. Otherwise, because in many cases we have data only from 20s or 30s, meaning tens of participants, at most hundreds. And if we want the model to work for billions of people, then we should have sufficient confidence that the model will work in scenarios that we have not seen yet. One approach that has proven successful for us is to detect candidate segments before we train a machine learning model. So that means rather than providing all data to machine learning when training, we only isolate the candidate segments. It has, for us, drastically cut down the data that is used in training, and so drastically cut down the false positive. But we ensure that when we detect these candidate segments, that we have no loss in recall. So that means all the actual segments of the event are included in the candidate segments. And as I said, a overriding concern for us has been that most of the data sets, I consider them pretty small with respect to how large of a population they need to work for. So therefore, we have tried to compensate. So next, I'll talk about evaluation. So basically, for evaluation, we prefer cross-subject evaluation, and the training and testing, it will be ideal if it's on independent data sets. And performance reporting, as I'll mention, that false positive analysis for us has been critical to see as to how this will work in real life. And we typically like to report it per day. And then there should be recall analysis and, if possible, temporal accuracy for start and end times. So I'll try to go a little bit quickly, given that we have only 15 minutes left, and I would like to leave some time for questions. But for the stress model, we evaluated it on independent lab study as well as, but then when it came to map to self-reports, we developed this accumulation decay model, a Bayesian network that models this, that when stressors arrive, we will observe a change in physiology. But then as time goes by, the effect of the stressor in terms of perception in mind may decay, but arrival of a new stressor can increase that, can accumulate the perception of the stress. And so that's what we use to map the stress, the physiological measure of a stress onto the self-reported stress. And we were able to achieve about 0.71 median F1 score. And that's pretty good, considering that the self-report of the stress itself has an internal consistency, alpha score of no more than 0.8 or 0.82, or about 0.84. So that means you can't expect to have 100% concordance with self-report. The best you can hope for is lower ratings. So for the cocaine use model, so as I said, so we had to isolate for the field study. In the lab study, it was clear as to when there was cocaine and when there was no cocaine. But for the field study, we had only self-report, and then we had this urine test. So what urine test did to us was that it confirmed which days we could confidently say that participants did not use cocaine. And so those are the days we used for false positive analysis. And all other times when they reported cocaine use and we could verify that we had good data during those times, then we used those for recall. So for 100% recall rate, we were able to achieve about 1 false positive per day in the field setting. So for the smoking cessation data, I described this data set. So what we do is that, see, out of our 61 participants, 33 participants did not lapse in those 3 days, and that was verified by their CO, CO report each day, each of those 3 days. So that's what we use for false positive analysis. And then for the, so that was 28 smokers, sorry. And then for the lapsers who lapsed, we used them for our recall analysis. So for first lapse, that means those who abstained but then lapsed. Our goal was to detect the first time they lapsed, because that is the clinically meaningful event, and that's what is the goal, to prevent first lapse in any smoking cessation program. So it was important to detect the first time that people lapse, and during the first lapse, they may not smoke the full cigarette, they may just take few puffs. And so it's a little more challenging to detect that first lapse. So we were able to detect this first lapse about 28 out of the 32 times. In other cases, either the sensor was not worn or that the data was lost. And but the number of false positive per day we had was about 1 false positive every 6 days. If we take each breath cycle, respiration cycle as our unit of assessment, then this will translate to about 0.002%. But as I said, that is, the percent false positive depends on your unit of assessment, and that can be widely varying depending on what the unit of assessment is. And therefore, I like to report the false positive as number of false positive in the entire day of wearing. So for the brushing and flossing, we were able to achieve about median recall of about 100% for brushing, and the number of false positive events per day was about 1 every 10 days. For flossing, because flossing involves a different kind of pattern, we were able to achieve 1 false positive every 25 days, because we don't have that many other hand-to-mouth gestures we do that looks like flossing. And the median recall for flossing was 75%, because many times the patterns that we need for flossing require both hands back and forth. And for the brushing and flossing, we also detected the start and end times, because remember we said we use the candidate segments, that means hand-to-mouth gestures, when people take the hand to the mouth for brushing and then they take the hand down. So we're able to identify the start and end time with pretty good accuracy for brushing, with an error of about 4.1%, and for flossing about 3.5%. So our key lessons is that objective and temporally precise labels for recall analysis are quite desirable. Self-reports have inherent noise, variability, lack of direct correspondence, and temporal imprecision that we need to account for. And false positive, I would prefer that it be done on the entire day of data and reported as false positives per day. And wherever feasible, we should evaluate the errors in locating the start end. So in general, I think there is this paradigm of 5 nines in the, when people provide this cloud services or internet services. If we want higher clinical utility for the markers that we are developing, we should also aim for 5 nines, which will be 1 false positive every 100 days. Now, recall is harder, because recall not only depends on the model's accuracy, but it also depends whether the sensor was worn during that time, whether the sensor had the battery during that time, whether the attachment was proper or not, right? And then the model failure. So So here the 5 nines will be I mean, a lot more challenging, but nevertheless something that we should shoot for. So so it has been hard for us to achieve the. It took a lot of work to achieve the sensitivity and specificity. Generalizability we don't even know until it is widely deployed, and reusability has not been any easier. So we have this. I mean, we have over this past 5 years of effort, we have developed this open source cloud software where we are trying to provide all the models, and I mean, and that can be run on large scale data sets. So, but our goal has been to make the data provide more open data sets, but then provide open data sets so that they're easily usable. And for that, we are trying to annotate it appropriately with the right metadata. And then for model reproducibility, we're trying to create appropriate provenance systems so that the models are appropriately annotated so they can be easily used by others. So if you're interested in any of this software, I mean, they are all available here. With that, I would conclude the talk. Thank you.